we saw that the relations between ensembles is determined by the Legendre-transform. Hence, it's not too surprising that all of the thermodynamic observables are tightly linked. Some of those links are given by the Maxwell relations. Let's first consider the microcanonical ensemble, or the NSV ensemble, and consider the second mixed derivative of the energy. We know we can change the order of taking the derivative of functions. For that particular example, del by del S, del E, del V is equal to del V, del E, del S. Now we know that the partial derivatives del E, del V is equal to minus the pressure, whereas del E, del S is equal to temperature. Hence, we obtain here a relation between del P, del S at constant volume and number of particles is equal to del T, del V at constant entropy and number of particles. Likewise, for the NTV ensemble, we obtain del S, del V at constant T and N is equal to del P, del T at constant S and N. And the NSP example, del T, del P at constant N and S is equal to del V, del S at constant N and P. And for the NTP ensemble, del S, del P at constant NT is equal to minus del V, del T at constant P and N, which defines the temperature coefficient of expansion being minus V beta P. Next to those Maxwell relations, there are further rules given by differential geometry. The first that we could use is the inversion rule, meaning that del y del x at constant z is equal to 1 divided by del x del y at constant z. First, we also have the chain rule saying that del y del x is equal to del y del w times del w del x. And we have a mixing rule saying that del y del x at constant z is equal to minus del z del x at constant y times del y del z at constant x. Using all those mathematical identities, you could imagine that there's only a limited number of free variables that have to be measured in order to characterize the system. As an example, let's consider the difference between the specific heat as measured at constant pressure versus the specific heat measured at constant volume. Typically, the first is easy to do, whereas the second involves to control the volume, which is more difficult. Now what we want to derive here is a measure for the specific heat at constant volume Cv from a measurement of Cp given some measured constants of a substance, which is the isothermal compressibility or the thermal expansion coefficient. We saw earlier that Cv is given by T del S by del T at constant V. In this case, S is dependent on T and the volume. Yet what we would like to know is what happens if we now keep the pressure constant. Hence we rewrite this equation to obtain T del S del T, where S now depends on the temperature and the pressure, which in turn is dependent on T and V. Now by taking the partial derivative, we get three terms, where the first, T del S del T at constant P, is the definition of the specific heat at constant pressure. For the second term, T del S del P at constant T, we use the Maxwell's relation, leading to the temperature coefficient of expansion, and a second term, dP dt at constant V, for which we obtain two other terms, one dV dt at constant P, again leading to the expansion coefficient, and the second term dV dP at constant T, which is related to the isothermal compressibility of the sample kappa T. All terms together now finally leads to the expression of Cp minus Cv is equal to T times V times beta P squared divided by kappa T. If we now further assume the substance is the ideal gas, for which the ideal gas equation holds, PV is equal to NKBT, we easily can derive these constants, beta P and kappa P, finally leading to the difference in the specific heat at constant pressure and constant volume is equal to NKB. This is a result that you might have seen at school earlier. As mentioned, those relations have a technological relevance as displayed here for water. For water, beta P, kappa T, and the specific heat at constant pressure have been well characterized. Knowing the relations that we just obtained, we can determine the specific heat at constant volume, which is experimentally very difficult to access. What you see for water is that Cv has a minimum at around 4 degrees centigrade, something that is known as the water anomaly. Given that the thermodynamic observables and potentials are strictly linked by derivatives, it's no surprise that there are way more relations you can think about. Bridgman has estimated how many of those relations exist. For the 10 variables that he considered, where all of those variables are linked by first derivatives, he came to the unbelievable number of 10 billion relations. A lot of those can be further simplified and classified, and that he has been done in the so-called Bridgman tables, where you can find in an easy way the relations between various parameters.